Most parents try to teach machine learning by jumping straight to coding tutorials and wonder why their kids glaze over in 5 minutes. The real problem? They skipped the foundation. Kids don't need Python syntax first. They need to understand what computers are actually learning and why. I'm Lakshmi Venkataraman, and today I'm walking you through methods that work because they build genuine understanding from the ground up. You're tuning in to the STEM Lab podcast. Quick note before we get rolling. Everything you're about to hear is researched, written, and fact-checked by real people on our team, but the voice delivering it is AI generated. We're transparent about that because we think it matters. If you've been listening for a bit, thank you for making this part of your week. And if you're new here, glad you found us. We drop new episodes every Monday, Wednesday, and Friday, all focused on helping you teach STEM concepts at home in ways that actually stick. Let's jump into it. When you're teaching machine learning concepts to children, you need a framework that transforms abstract algorithms into tangible experiences they can manipulate and understand. This guide shows you exactly how to explain machine learning to kids using developmentally appropriate methods that build genuine conceptual understanding rather than superficial familiarity. You'll learn scaffolding techniques that work across age groups, from concrete sorting activities for elementary students to supervised learning experiments for middle schoolers. Expect to spend 30 to 60 minutes on each method, depending on your child's age and prior coding exposure. These approaches align with standards for data analysis and computational thinking while preparing students for the AI literacy demands of their future careers. Let's talk about what you'll need to get started. For foundational materials, gather a large collection of sortable objects, buttons, toy animals, Lego bricks, at least 30 pieces with varying attributes. You'll also want index cards or sticky notes for labeling categories and age-appropriate dataset examples like printed photos, trading cards, or digital image folders. If you're working with kids ages 8 and up, you might want some optional technology. A computer or tablet with internet access is helpful. Google Teachable Machine is fantastic. It's free, browser-based, no installation required, and works on Chrome OS, Windows 10 and 11, and Mac OS 10.14 or later. Check the link below to see the current price for a Raspberry Pi 4 Model B with 4 GB RAM minimum if you want to do hands-on machine learning projects requiring Python 3.9 or later. A camera or smartphone for capturing training images rounds things out. As far as prerequisites go, kids ages 5 to 7 just need a basic understanding of patterns and sorting. Ages 8 to 10 should have some familiarity with block-based coding like Scratch. For ages 11 and up doing advanced activities, introductory Python experience helps. There's a guide on how to transition from screen-free coding to Scratch and Python programming linked below. Now, let's get into the first method. Start with physical sorting activities to build pattern recognition schema. Before you introduce the term machine learning, you need to establish the cognitive foundation, pattern recognition, and classification. I've watched hundreds of sixth graders struggle with machine learning concepts because they jumped straight to algorithms without understanding the fundamental skill computers are mimicking, the ability to group similar things based on observable features. Spread your collection of objects on a table and ask your child to sort them however makes sense. Don't provide categories initially. After they've created groups by color, size, shape, function, discuss their decision-making process. What features did they notice? How did they decide which group each item belonged to? Now, introduce a critical shift. Ask, what if I showed you a new object? How would you know which group it goes in? This question scaffolds the concept of predictive classification, which is the core function of supervised machine learning. Have them articulate their sorting rules explicitly. If it has 4 legs and fur, it goes in the animal group. For ages 5 to 7, keep this concrete with 2 to 3 obvious categories. Ages 8 to 10 can handle 4 to 5 categories with overlapping features that require multiple decision points. Ages 11 and up should wrestle with ambiguous cases where features conflict, introducing the concept of confidence scores and error rates. This hands-on method demonstrates how to explain machine learning to kids by letting them experience the classification challenge before naming the computational solution. They're building mental models of feature extraction and decision boundaries, the same concepts data scientists use when training algorithms. Moving on to the teacher-student framework for supervised learning. Once your child understands sorting by rules, introduce the machine learning paradigm. Computers can learn sorting rules from examples instead of being explicitly programmed. This is where the teacher-student metaphor becomes powerful pedagogical scaffolding. Explain it this way. When you sort objects, you're the expert who already knows the rules. But what if you had to teach someone who'd never seen these objects before? You'd show them examples, right? You'd say, this is a dog, this is a dog, this is a dog, and eventually they'd recognize new dogs without you telling them. That's supervised learning. The computer is the student, the training data is your teaching, and the labeled examples are the lessons. I use this framework constantly in my classroom because it transforms the computer from a mysterious black box into a relatable learner, making mistakes and improving over time. Create a simple supervised learning activity. Sort 20 objects into 2 categories, but keep 5 hidden. Have your child create a teaching set by clearly labeling examples. Then ask a sibling or partner to learn the rules from just those labeled examples and classify the hidden objects. Discuss accuracy and what happens when the student sees unusual examples. For older students, ages 11 and up, extend this to discuss training data quality, bias in examples, and overfitting, what happens when you memorize specific examples instead of learning general patterns. These aren't simplifications, they're the actual challenges machine learning engineers face daily. Understanding supervised versus unsupervised learning opens the door to more complex AI concepts. There's an article on what is supervised versus unsupervised learning linked below that explores these distinctions in depth with age-specific activities. Next up, building image classification models with visual tools. Now you're ready for hands-on model training using tools designed for educational machine learning. Google Teachable Machine has become my go-to recommendation for ages 8 and up because it makes the training process completely transparent. Students see the computer watching their examples and can immediately test predictions. Here's your structured approach. Choose a binary classification task first, 2 categories only. Have your child collect 15 to 20 images for each category using the webcam or uploaded photos. Start with highly distinct categories like dogs versus cats, apples versus oranges. The visual feedback is immediate. The confidence meter shows how certain the model is about each prediction. The learning happens when predictions fail. Intentionally test edge cases. What if you show it a picture of a dog and cat together? What about a cartoon dog versus a real photo? These failures aren't problems, they're pedagogical gold that reveals how the model learned and what features it's using. For ages 8 to 10, stop here and discuss why it got confused and what you could do differently. Ages 11 and up should retrain models with more diverse training data, experiment with different numbers of examples, and document how accuracy changes. This directly mirrors the iterative process of professional machine learning development. Some quick specs for Teachable Machine. It's browser-based, Chrome or Edge recommended, requires a stable internet connection, exports models for offline use in Scratch or Python projects, and is completely free with no subscription. It works on any device with a camera, Chromebooks, tablets, Windows, or Mac laptops. Processing happens in browser, so older devices from 2015 or later may experience lag with complex image sets. This tool bridges the gap between abstract concepts and hands-on creation, giving students genuine experience with the train, test, deploy workflow that defines applied machine learning. For students ready to progress beyond visual tools, there's a guide on how to build your first machine learning model with kids linked below for Python-based approaches. Let's talk about demonstrating feature extraction through "What did the computer notice?" games. The most common misconception I encounter when teaching machine learning is that students think computers see images the way humans do. They don't grasp that algorithms extract mathematical features, patterns of pixels, edges, colors, rather than understanding semantic meaning. How to explain machine learning to kids effectively requires making this feature extraction process explicit. Create a game after training any image classifier. Show the model various test images and ask, what do you think the computer is noticing? Is it the shape, the color, the background? This develops computational empathy, the ability to think from the algorithm's perspective. Try this revealing experiment. Train a model to distinguish inside versus outside photos, then test it on images with unusual lighting or mixed settings. Students quickly discover the model might be keying on lighting or background colors rather than actual location markers. This isn't a failure, it's a profound lesson about algorithmic decision-making. For ages 11 and up with Python experience, extend this to numerical features. Collect simple data sets like height and weight measurements or temperature and ice cream sales and plot them on graph paper. Physically draw dividing lines between categories. They're now visualizing decision boundaries, the mathematical rules that separate classes. Challenge advanced students. What features would you need to identify handwritten numbers? What makes a 7 different from a 1? They'll suggest slant, loops, line intersections. These are edge detection and shape features that real computer vision algorithms use. You've just explained convolutional neural network concepts without the jargon. This metacognitive practice, thinking about what the algorithm is thinking, prepares students for AI literacy far beyond coding. They're learning to question algorithmic decisions, recognize bias sources, and understand limitations. For deeper exploration of how neural networks process information, there's a guide on neural networks explained for kids linked below. Now, scaffolding from concrete examples to abstract concepts with progressive complexity. Developmental psychology research confirms what I see in classrooms daily. Children build understanding through concrete to abstract progression. When teaching machine learning, this means starting with visible, manipulable examples before introducing terminology or mathematics. Your learning path should follow this sequence across weeks or months, not a single session. Phase 1, for ages 5 to 8, physical sorting, guess the rule games, exploring patterns in everyday objects. No computers, no code, just cognitive skill building. Phase 2, ages 8 to 10, visual machine learning tools like Teachable Machine, binary classification tasks, discussing why predictions fail, connecting computational processes to their physical sorting experiences. Phase 3, ages 11 to 13, training data bias, multi-class problems, accuracy metrics, introduction to training and testing splits, beginning to use machine learning terminology formally while maintaining hands-on model building. Phase 4, ages 13 and up, text-based machine learning in Python using simplified libraries, understanding algorithms as mathematical functions, and discussing real-world machine learning applications and ethical implications. Do not skip phases or rush to coding. I've seen enthusiastic parents jump straight to Python machine learning tutorials with 10-year-olds who have no conceptual foundation. The children memorize code syntax but can't explain what the model is doing or why. That's not learning, it's cargo cult programming. Between each phase, revisit earlier activities with increased complexity. Return to the physical sorting task, but now have students think consciously. What features am I using? How confident am I in this classification? What would happen with ambiguous examples? They're applying machine learning vocabulary to concrete experiences, which cements understanding. This progressive approach aligns with how professional data scientists actually learn, starting with statistical concepts, moving to simplified models, gradually building toward complex architectures. You're not just teaching machine learning, you're modeling the learning process of the field itself. For students ready to move from block-based to text-based machine learning programming, there's a guide on Python versus Scratch for teaching AI to kids linked below with detailed transition strategies. Let's discuss using real-world applications to build motivation and context. Abstract learning rarely sticks without meaningful context. When you ground machine learning concepts in applications students encounter daily, you transform interesting activity into relevant skill I need to understand my world. Discuss machine learning systems your child interacts with regularly. How does Netflix know what shows to recommend? How does their tablet's photo app group pictures by faces? How do voice assistants understand spoken commands? Each example offers teaching opportunities. For recommendation systems, explain it like this. Remember when you sorted objects by features? Netflix does the same thing. It puts you in groups with people who liked similar shows, then recommends what those groups watched next. You've just explained collaborative filtering using their sorting schema. For facial recognition, the camera is looking for features like distance between eyes, nose shape, mouth position, just like you noticed features when sorting toys. That's facial landmark detection made tangible. Ages 11 and up benefit from discussing machine learning ethics and limitations in these applications. When does algorithmic recommendation create filter bubbles? What happens when training data includes biased examples? I've led dozens of middle school discussions where students become genuinely engaged in these questions because they're about systems affecting their actual lives.
Connect machine learning to potential career paths. Data scientists, machine learning engineers, AI ethics researchers, algorithm auditors. These roles didn't exist 20 years ago and are now among the fastest growing tech careers. The Bureau of Labor Statistics projects computer and information technology occupations to grow 13% through 2032, with AI specializations leading demand. For students pursuing hands-on AI applications, there's a collection of AI project ideas for kids linked below, organized by skill level and learning outcome. Moving on to creating iterative training experiments to demonstrate model improvement. The most powerful way to explain machine learning to kids is letting them experience the iterative refinement process that defines actual machine learning development. Create structured experiments where students train a model, test it, analyze failures, and retrain with improvements. Here's a concrete experimental framework for ages 10 and up. Experiment 1. Baseline. Train an image classifier with just 5 examples per category. Document accuracy on 10 test images. Most models will perform poorly. That's the point. Experiment 2. More data. Add 10 more examples per category. Retest with the same test images. Students immediately see accuracy improvement, connecting more training data to better performance. Experiment 3. Data diversity. Add examples with different backgrounds, lighting, angles. Test again. Discuss how diverse training data creates more robust models. Experiment 4. Edge cases. Intentionally test difficult examples like blurry images, unusual angles, objects partially obscured. Document where the model still fails. Maintain a lab notebook throughout this process, just like scientists do. Students record hypotheses. I think adding more examples will improve accuracy. Methodology, exactly what they changed. Results, accuracy percentages, and conclusions, what they learned. This isn't just machine learning education, it's training in the scientific method and experimental design. For ages 13 and up with programming experience, extend this to hyperparameter tuning. What happens if we train for more iterations? What if we adjust the learning rate? They're now engaging with concepts that machine learning engineers manipulate daily, demystifying the magic of neural network training. This experimental approach solves a critical pedagogical challenge. Students often think machine learning models either work or don't work, missing the optimization mindset that defines the field. By repeatedly improving a model through deliberate changes, they internalize that machine learning development is iterative refinement, not one-shot programming. Students building more advanced machine learning projects will benefit from understanding how to organize progressive learning paths. There's a guide on how to design a progressive STEM learning path linked below that offers frameworks for long-term skill development.
Now, connecting machine learning to other STEM skills for comprehensive understanding. Machine learning doesn't exist in isolation. It draws on mathematics, statistics, logic, and domain knowledge. How to explain machine learning to kids most effectively means building connections across their broader STEM education. For mathematics integration, discuss how classification creates boundaries in data. Plot simple 2D data sets like height versus weight or age versus bedtime on graph paper and physically draw lines separating categories. You're visualizing linear separators, the geometric foundation of many machine learning algorithms. For statistics integration, remember that every machine learning model makes predictions with uncertainty. Discuss confidence scores as percentages. The model is 85% sure this is a dog. Connect this to probability concepts they're learning in math class. When is 85% good enough? When do we need 99% confidence? For logic and coding integration, if your child has experience with screen-free coding toys or block-based programming, connect conditional logic to machine learning decision-making. Remember if-then statements? The model is creating hundreds of if-then rules automatically by learning from examples. For engineering integration, machine learning models are deployed in systems, robots, apps, smart devices. Students with robotics kit experience can explore how machine learning enables robot vision, object recognition, and adaptive behavior. The LEGO Mindstorms platform now supports basic machine learning integration through cloud APIs. I've observed that students with interdisciplinary STEM exposure grasp machine learning faster because they have richer cognitive schema to connect new learning to. If your child has built circuits, programmed robots, or designed 3D models, explicitly reference those experiences when teaching machine learning. Remember designing that gear in Tinkercad? Machine learning can optimize designs automatically by learning what features make strong parts. This comprehensive integration prepares students for the reality of applied machine learning, where success requires domain expertise, coding skills, mathematical understanding, and systems thinking working together. For parents building holistic STEM education at home, there's a guide on how to build a home STEM lab linked below with infrastructure planning for progressive skill development. Let's cover some pro tips and common mistakes. Start with binary classification before multi-class problems. The cognitive leap from this or that to one of many options is significant. Master two-category tasks first. Avoid the black box trap. Don't let machine learning tools become magic you click without understanding. Always ask, what is the computer learning? What features is it using? Why did it make that prediction? Prioritize transparency over impressive results. Embrace failure as pedagogy. The most powerful learning happens when models fail in interesting ways. A model that's 100% accurate on test images teaches less than one that's 80% accurate with documented error patterns you can analyze together.
A common mistake I see constantly. Parents focus on accuracy percentages as the success metric rather than conceptual understanding. Your child can train a 95% accurate model by following steps without grasping anything about feature extraction, training data, or decision boundaries. Process matters more than outcomes at this stage. Don't rush to neural networks. Deep learning is exciting, but jumping there too quickly skips foundational concepts. Students need to understand simple classification before they're ready for network architectures, layers, and backpropagation. Technical consideration: many machine learning tools require stable internet and modern browsers. Test tools on your devices before planning lessons. Check the link below to see the current price for a Raspberry Pi 4 Model B. It offers an affordable standalone platform for running machine learning models offline using TensorFlow Lite, though setup requires adult technical comfort with Linux systems. Age-inappropriate depth warning. I've reviewed curricula that introduce gradient descent mathematics to 10-year-olds. Unless your child has exceptional mathematical interest and algebra proficiency, this creates confusion rather than understanding. Respect developmental readiness. Let's address some frequently asked questions. What age should children start learning about machine learning? Children can begin learning foundational machine learning concepts, pattern recognition, and classification as early as age 5 through physical sorting activities and guess the rule games. Around age 8 to 10, they're developmentally ready for visual machine learning tools like Teachable Machine that train actual models. Text-based machine learning programming in Python typically becomes accessible around age 11 to 13 for students with prior coding experience. The key isn't age alone, but whether the child has prerequisite skills in patterns, basic logic, and for ages 8 and up, some block-based coding exposure first. You're teaching computational thinking first, then adding machine learning as an advanced application of those skills.
What's the difference between teaching AI and teaching machine learning to kids? Machine learning is a specific subset of artificial intelligence. It's the technique of training computers to learn from examples rather than explicit programming. When teaching kids, machine learning offers more concrete, hands-on learning opportunities because students can train actual models and see immediate results. Broader AI education includes rules-based systems, logic, robotics, and computer vision. I recommend starting with machine learning because it's tangible. You'd train a classifier, test it, see it work or fail, compared to abstract AI philosophy. For comprehensive coverage of both, there's a guide on how to teach kids AI and machine learning linked below. Can machine learning education happen without expensive equipment or software? Absolutely. Some of the most effective machine learning teaching requires zero technology. Physical sorting activities, pattern recognition games, and teaching a student role-playing exercises build genuine understanding using household objects. When you're ready for digital tools, Teachable Machine like browser-based platforms are completely free with no installation required. Check the link below to see the current price for a Raspberry Pi 4 Model B. It costs around $55 and runs sophisticated machine learning models, making it far more affordable than assuming you need high-end computers. The limiting factor is rarely equipment, it's pedagogical approach and having a structured learning path that matches the child's developmental stage. To wrap things up, teaching machine learning successfully requires starting with concrete, manipulable experiences before introducing algorithms or code. You've learned how to explain machine learning to kids using physical sorting activities that build pattern recognition, the teacher-student framework that clarifies supervised learning, hands-on model training with visual tools, and progressive complexity that respects developmental stages. These methods align with science standards while preparing students for AI literacy in their academic and professional futures. The experimental, iterative approach you've explored mirrors how professional data scientists actually work, creating models, analyzing failures, and refining through repeated cycles. Whether your child is 5 or 15, focus on conceptual understanding over technological impressiveness, embrace instructive failures, and build connections across their broader STEM education. For students ready to advance beyond these foundations, there's an AI Concepts Every Child Should Learn checklist linked below to identify next steps in their machine learning education journey.
That's it for this episode of the STEM Lab podcast. Thanks for spending this time with me. We've got new episodes coming your way every Monday, Wednesday, and Friday. If you got something out of today's episode, I'd really appreciate it if you left a 5-star rating and a quick review. It's honestly one of the best ways to help other parents and educators discover the show. And hey, hit subscribe or follow so you get notified the second a new episode goes live. See you next time.